Hello, welcome to this video. My name is Wuyang Chung. In this video, I'll talk about using capability to implement memory bounce check. So here is the outline. First, I'll compare the two memory bounce check approach. That is the object-based approach and the pointer-based approach. And then I'll add the capability-based approach in this comparison table also. And then I'll talk about the capability-based approach in more detail. Then I'll talk about how the capability-based approach support temporal safety check. And then I'll talk about how it supports the principle of exclusive thread local data. And then finally, the conclusion. So here is a comparison of object-based approach and pointer-based approach. So in both approach, they all need to store some metadata about the object in order to do the bounce check. So in object-based approach, the metadata is associated with the object, so the pointer format is not changed. Since the pointer format is not changed, so it is compatible with all programs. For pointer-based approach, the metadata is associated with the pointer. Usually, it is stored along with the pointer, so the pointer becomes bigger. So that's why it is also called fat pointer approach. Since the pointer format changed, so it is not compatible with old programs. For the cost to get the metadata in object-based approach, it usually needs a lot of memory or CPU time to get the metadata. For pointer-based approach, the cost is low because the metadata is stored along with the pointer. So for spatial safety, it is supported by both approaches. For temporal safety, in object-based approach, it usually uses quarantine to support the temporal safety check. So when an object is freed, it will be moved to quarantine state for some time. And during this time, if the object is referenced, it will trigger an error. And after the quarantine time is up, the object will then moved to normal state. After that, the compiler can no longer detect the temporal safety violations. For pointer-based approach, it usually uses the garbage collection or lock and key method to do the temporal safety check. For the garbage collection method, it is the compiler need to scan the program and find for all the pointers in the program and to see if the pointer is pointing to the freed object. In lock and key method, it needs two more fields in the metadata, so it will make the pointer even bigger. So for the principle of intentional use, for object-based approach, it is not supported because in object-based approach, it only knows that the pointer is pointing to some object, but it did not know, or it does not know if the pointer is pointing to the intended object. For pointer-based approach, it is supported because the pointer can only pointing to the object specified by the metadata that is stored along with the pointer. For principle of exclusive thread local data, this principle means that a thread can only access its own thread local data. It cannot access other threads' local data. And for object-based approach, it is not supported. The reason is the same as above. That is, since it did not support principle of intentional use, it also did not support the principle of exclusive thread local data. For pointer-based approach, it depends on the implementation. So now let's see the capability-based approach. In capability capability-based approach, a pointer is followed by a capability. So the pointer format is changed, so it is not compatible with all programs. For the cost to get the metadata, the cost is low because to get the metadata is simply a table index operation, and I'll talk about it later. And for spatial safety, this is also supported in capability-based approach. For the temporal safety, capability-based approach uses capability revocation to support temporal safety violation check, and I'll talk about it later. So for the principle of intentional use, it is supported in capability-based approach. In capability-based approach, the pointer can only access the object that's specified by the capability. So for the principle of exclusive thread local data, it is supported, and I'll explain it later. So here is the pointer format for the capability-based approach. The pointer is followed by a capability, and the capability by definition is permissions plus a unique object ID. In capability-based approach, all the objects in the program will have an entry in the object metadata table that stores the start address and the end address of the object. Since every object in the program has an entry in this table, so the index to this table can be seen as the unique object ID. So here it is actually the unique object ID is actually an index to the object metadata table. So for permissions here, the permission is used to check the read, write, execute permission. But for bounce checking, we don't need to check permission. We only need to check if the pointer is within the object range. But anyway, we still need something to prevent the capability from being forged. Here I'm using the tagging to do that. In this method, the capability will have a tag field, and the metadata also has a tag field. And the capability is valid only when the tag in the capability is equal to the tag in the metadata. And the tag must have at least 4 bits because the probability of false negative will be lower with more bits in the tag. So in capability-based approach, a pointer is followed by a capability that contains a tag field and index field. So when the pointer is dereferenced, the compiler will do the following check. First, it will check that the tag in the capability is equal to the tag in the metadata. This is to make sure that the capability is valid. And then it will check that the pointer is within the range of the object. So now let's look how it supports the temporal safety check. So normally in a program, there will be multiple pointers that pointing to the same object. So in this figure, you can see that pointer A and pointer B both pointing to the same object. So they are followed by the same capability. So when an object is freed, the free function will not only free the object, it will also change the tag in the metadata. Since the tag is changed, so the capabilities that pointing to this metadata are all revoked. So the capability becomes invalid, and then the pointer becomes dangling pointer. So if the program then tries to dereference this pointer, it will trigger an error because tag in the capability is not equal to the tag in the metadata. Also, if the program tries to free the object again, it will also trigger an error because tag in the capability is not equal to the tag in the metadata. So previously in the slides, I only mentioned one metadata table. Actually, the program will have two kinds of metadata table, that is the global metadata table and local metadata table. The global here means that the data that can be accessed by all threads in the process. The local here means that the data that can only be accessed by one thread in the process. So a process has one global metadata table that is used to store the metadata for objects on global variable heap or constant data. And we need a lock to protect this table because multiple threads can access this table. And each thread in a process has a local metadata table, and this table is used to store the metadata for objects on the stack or TLS. So we do not need a lock for this table because only one thread will access this table. So the actual pointer format in this approach is that the pointer is followed by a capability, and the capability contains a tag, a G or L bit that indicate whether the index is pointing to the global metadata table or local metadata table. So now let's see how it supports the principle of exclusive thread local data. As mentioned previously, this principle means that a thread can only access its own thread local data. It cannot access other threads' local data. So in this picture, you can see that the pointer is followed by a capability that pointing to a local metadata table. And as you can see, only one of the local metadata table will have a tag that's equal to the tag in the capability. So it means that only thread B can dereference this pointer. If thread A tries to dereference this pointer, it will trigger an error because the tag are different. So conclusion. In capability-based approach, the pointer is smaller than the fat pointer-based approach, and it can get the object metadata with very low overhead because it is just a simple indexing operation, and it can detect temporal safety violations by using capability revocation. So when doing main copy, there is no need to propagate the metadata for the pointers in the buffer, since the metadata is in a separate table. So to support bounce checking for objects on stake, in function prolog, the compiler will insert the metadata of objects on the stake into the local metadata table, and in function epilogue, the compiler will remove those metadata from the local metadata table, and this is how the bounce check for objects is done in the capability-based approach. So that's all I have about this video. So thank you for your time.